charge tape revisited. So the point of this lab is to extend on lab one and treat the piece of tape as a distribution of charge to find the excess charge on each of the tapes. So we're using the definition of E in Newton's second law. And we found that this was our experimental value for the experimental one, and this was the computational value for the charge. The difference is because we're treating the tape as a continuous object for the experiment, but as a discrete object for the computational model. So these are the equations that we're using, essentially just the definition of E, so Fe equals QE, and we set the net force equal to zero, and the only other force is the gravitational force. We're also using this, the E rod equals all of this, because we're treating the piece of tape as a thin rod of evenly distributed charge. Um, and so we have a couple assumptions, namely that the two tapes are identical and it's a single homogeneous charge. And they can be treated as continuous charge distribution like a thin rod or a discrete distribution with 10 charges for the computational model. So for the experiment, the system is the top tape and the surroundings is the bottom tape and the Earth. These are our initial conditions. Essentially, what we did is we just held the one tape below the other and see how much the other one rose. And we found that that was about 1 centimeter of separation at its highest point. So after that, I set the net force equal to zero. So the force electric equals Fg, and then so QE equals mg. And recognizing that since the two tapes have the same charge, we can just set that equal to Q and solve for Q. And so from that, we get 1.4 times 10 to the negative 8 coulombs, which is reasonable because it's between the range that we were expecting. So for the code, we use the same initial conditions, and essentially we just use the function from lab 0 to calculate the E field at a random location. And then we iterated through each particle on the top tape and each particle on the bottom tape to find each net E field on each particle on the top tape. And then we summed all of those to find the net force in the top direction, supposed to cancel the net force, the force from gravity. So this is some of the code. Right here, you can just see that we're defining the constants. Here, we're creating the top tape and bottom tape objects, and here's the function to calculate E field. Right here, we're iterating through each charge, and at the bottom is just drawing the arrows. So these are the results. As you can see, we have all the bottom tapes here and all the top tapes here, and these are all the forces exerted on the top tapes. And then the net forces are represented by the white and yellow arrows. So as you can see, they cancel out right here. And so from this, we found that the net charge on the top tape or on each tape was 1.38 times 10 to the negative 8 coulombs, which is also very close to what we expected. So in both cases, we used the same formulas, and they fell between a reasonable range, but the experimental values are more accurate since the tape is more like a continuous charge distribution compared to a discrete distribution because there are so many atoms inside of the tape. So we have a couple of assumptions. The first is that they have an even distribution of charge. For instance, you could have more charge on one side than the other, but we're assuming that that's not the case. And we're assuming, so for the experimental, that's a continuous distribution, which is actually not true because there's a finite number of atoms in the tape. But for the computational model, there's also the error that there's only 10 particles, which is clearly not true. And so we're also assuming that the same net charge and that we accounted for all the forces on the tape. So we had a very small difference, about 1 times 10 to the negative 9 coulombs. And this is likely because we treated one as a continuous distribution, the other as a finite discrete distribution. And there are other sources, just like the tape being handled, they weren't perfectly parallel, some inaccurate measurements surrounding errors, other forces. The distribution charge wasn't actually even, and n equals 10 is too small, that we should use a much more realistic value, like billions of particles. So if we had treated them like a single point charge, we would find that our charge from lab one was actually way higher, and it's actually around 3 times greater if you take this ratio, for both of them. And so the reason for this is because the ones that are further from the center contribute to the less net force in the y direction than particles closer to the center. The x components just cancel out because of symmetry. So that means you need more net charge to obtain the same separation when you're treating it as a charge distribution horizontally. So the values obtained in this lab are more likely to be true because the tapes behave more like a thin rod of charge compared to a point charge. And it's useful because we're at very small distances compared to very large distances where it's appropriate to use a point charge estimate. So in conclusion, these are values that we found for the charge, and they were much greater than that obtained in the first lab. And then rather than using Coulomb's law, it's easier to just calculate E using calculus and then use F equals QE to find the net force. Thanks.